Before we get started, I want to ask, for example, Eric, to you. Uh, have you tried to find out the way that we could do those who have Windows systems, if they have iOS 10 and VMware? Uh, have you tried to run?
Using Oracle's VirtualBox,
Uh-huh.
I was able to find a tutorial online for install OS X or send into a VM. I'm not sure if it's functionality using whatever program you have that you want us to install, but it's a working copy of iOS X. I'm able to surf the web, I'm able to do pretty much everything that I've never owned a Mac, so I'm going to test it. I'm able to surf the web and do most normal things in that environment.
Oh, I see. So from your test, you could see like Mac OS looks running
I have to be a little
so
patient,
far.
but I think that's just a RAM issue. I think if I upgrade
Oh,
the
I
RAM,
see.
then it's only have 8 gigabytes, and I allotted 4 gigabytes for the VM. But
What is the memory size of yours? 8 gig or 4 gig?
my total is 8 gig, but for the
8 gig.
VM I allotted 4.
Oh, I see.
So I don't know, maybe if I upped it or I just didn't up it totally, but it's a little slow, but other than that, it's operation.
Anyway, the emulation, although you do have apps development and try on your emulator on your Mac desktop or laptop, it needs emulator. If you have a device itself, for example, if it runs for iPhone or Apple Watch or Mac TV, then it runs very quickly. Other than that, it is visualized over the emulator of, for example, your Mac TV, Apple TV, or Apple Watch, or iPhones. Anyway, we can. That is only for the development purpose. It's not for usages. So we will do that. As a summary, we appreciate to Eric's attempts. If you have VMware or Oracle virtual machine, right? Oracle virtual machine. And then what is the OS?
The OS is OS X is 7. I put
Yosemite? Is it Yosemite? Is it called Yosemite?
an email to everybody on Black.
Oh, great. Did you do that to me? Or excluded? I haven't received. Oh, did I?
I think
No.
I might have taken you out.
No, we received
Yeah, I everybody else
But me.
copies.
Oh, that is the reason. Okay. Oh, we have a new ladies.
Yes.
I haven't met. Did I meet you?
No, this is my first name.
Oh, first time? And I think but we somehow, I probably remember your name. What is your name, by the way? Huh? Albanaco? Albana Blanco, yeah. So you're new here. So you commute from Bronx? Oh, okay. So back to Dobbs Ferry campus would be okay? Okay. The reason for that is, as I expressed in the syllabus, first 2 lectures, which means the 2 weeks lecture, will be held here in Manhattan. And then from third week, we will switch back and forth, which means the third week I'm going to be at, we all go back to Dobbs Ferry campus. And then there's a third. And fourth week, we will come back here. So every other week, we meet at one campus. And another week, we at another campus. Reason I'm doing that is because some students purely, I mean, this is far from here, like, for example, Orange County. And also, some students prefer to be here, Manhattan, because they want to come to Long Island or Berkeley. So this is my resolution. We don't do this every semester, but we'll try to do that. And also in this semester, by the way, we have a lot of Bronx openings. I mean, courses are offered at Bronx also. Some veterans can take a big benefit by taking courses in the city area than Westchester County. So they receive, some students receive several thousand more dollars per month. So we try to help them. Hey, Chris. All right. Another announcement is, yeah, so you need to get ready to follow my lecture. First, this class will deliver two big topics: apps development for iOS. Not not all of you have Mac version. Some Windows. By the way, we need to have laptop if you have it. That's fine. Yeah, not for today. Yeah, you're lucky. Which one? Are you Windows or Mac? Oh, great. Yeah, especially for this semester, Mac OS is really crucial. If you do not have it, still possible. The Eric made an announcement. I mean, sent it out in email. I would receive the same email from him so that I can copy to our online students as well. So if you do not have a Mac, then you can set up a virtual machine and install iOS, whatever the version that you could have. Okay. So from there, we'll work next time. I will let you know which one that you need to download, how to install, and therefore we need to make first a simple Hello World like app, but much better than Hello World, if as far as you are working on apps, I mean smartphone apps. Okay. Meanwhile, for today, it's not really necessarily. Oh, we have some more outlets, many more. Yeah. You do not want us to wait for you. All right. So this lights, foundations of lights and sound is very important. Not only wireless sensor networks, but iPhone, for example. Anything that you want to communicate over the wireless media. There's no media. Wireless means there's no media, right? Let's say there's a wireless media. And on top, you want to send some messages. Okay. And the wireless signals or wave propagates to the target device. Your smartphone, there's no such a smartphone only communicated over wired media, right? All wireless. Therefore, we call it smart, maybe, rather than wireless. So foundations for all the communication. iPhone, Android phones, any smartphones, or sensors, any type of wireless sensors like GPS, wireless cameras, or any sensors, temperature or chemical sensors, or physical movement detection sensors, um, any sensors that you could find from future vehicles, automobiles. So, um, so this class gives you a little bit of the future technologies. So understanding light and sound, the characteristics or nature of lights. Lights, therefore, you can see. Right now, you can see me. How it is possible? Because you understand the lights. You can hear me. How you can hear me? You can hear me if you understand the nature of sound. Although we have not heard any physics background of lights and sounds so far, there's our gift, right? So we had no problem of seeing or hearing. But knowing such foundations, I mean fundamental physics, you can understand the devices much better. So today is not purely computer science course. It's not purely cybersecurity course, but a little bit physics. But I do not give you any mathematical formations, formulas, or physics theory. It's a little bit fun story. Okay, so let's take a look. We can hear basically sound, right? Sound. Sound. Good. What is the sound? So, so he talked to us when he comes in, so we can hear what he says. We don't say it sound in general, but we hear his footsteps, right? That's definitely sound. Footsteps. All needs sound. What is the sound? As you can see here in the slide, it is a physical energy. Some energy. Energy is transmitted. So as energy transmitted, there is this. It's not transmitted in a straight line. There's some wave in wave form. Wave. From your basic understanding, what type of waves have you known so far? Waves. In high school, middle school, some mathematics. Sine waves, right? Sine waves, cosine waves, they look similar, right? Only difference is a little bit shift. We call both sine waves. Some waves. If it is not really sine waves, but a different amplitude, so that you can hear different magnitude, and we identify by such amplitude or magnitude, so that it delivers you some more semantics, so we can communicate. There's some energy, okay? So the energy transmitted over the air. Over the air. Air, therefore, there's some media, right? Air is not something empty. Air, therefore, we feel some gravity. If there is no air, then what happens? You don't have to stand, right? You can pose whatever you want. Once you jump, then there's no way that you can get down to the ground. That is what happens, right, in the spacecraft. You know that, right? Once they up in the air, in order to get down, then they need to have some energy to push his or her body against. So there's some media in the air. Okay. So that much some obstacles if you want to transmit. If there is no air, then what happens? Because there is no obstacles, no resistance. Maybe signals can reach much further because there is no resistance. If there is resistance, then it needs a big energy. Therefore, through that energy, any signal, for example, sine wave, needs to penetrate all the way through. As it propagates, the energy will reduce. So less energy, therefore, eventually your signal will stop somewhere. So when you shout here, your voice, it doesn't reach forever, right? If you shout here, then no one can hear you from outside. First of all, there is a big resistance, glasses of this building. So it cannot penetrate further. But if some other sound, which might have much stronger energy than our voice, then somebody can hear from outside either. I mean, right? What kind of? Some explosion, right? Something exploded here, then somebody can hear from outside also. So each sound has different idea, has different energy. So it can reach to different distance. If sound does not have enough energy, but carrier itself has strong energy, then it can travel further. For example, data. How often do you send the data from your iPhone? You send some text, right? Text doesn't have energy. Do you think text some moves, so it has some energy? If there is energy, then if it moves so fast, then you can feel some temperature also. If you touch text, anybody feel any? No, nothing, right? It has no energy. No energy, then no transmittable. Sound, there may be some energy, right? Therefore, if you talk much, means you consume that much energy. Therefore, you need to eat more. Talking sometimes is kind of a labor, right? Anybody had that experience? If you talk too much, then you feel hungry. Why hungry? Because you spent energy. Every time when you generate sound, acoustic or vocal sound, so it requires some energy. So from your body, that much consumed. Text, back to text messaging, no energy. How come text message can be transmitted from me to where? It's another media, right? Another media, carrier. So there is another signals. That signals carries text on top. Your cell phone has always some signals emitted. Therefore, your cell phone needs battery. If you send the more text or more data sent out or received, the battery runs out quicker, right? We all know that, right? So energy is very, very important. And studying about energy is nothing but physics, right? But anyway, there is an energy, sound, acoustics. Acoustics is some physics about sound. So we will look at a little bit of those. Uh, Psychoacoustics. It's a psychological response to acoustic stimuli. So some somebody study about philosophical analysis based on um, vocal level, like level of loudness or pitch, depending upon some amplitude and timbre, level of timbres. So we can hear some, just depending upon our um, analysis purpose. Sometimes we can simply see the sound itself, or some other times acoustics. Sound, as we looked at, it is nothing but a little bit of a wave. Sound wave, therefore there's a light wave also. As I said last time, about 300 years ago, Newton says light is a particle. So we have another slides for that when it comes to lights. At that time, some of the scientists says, maybe that is some kind of wave. But Newton has strongest power at that age. He has more power than the king. It's a king-like power. So no one can argue against his theory. But anyway, light has a light wave also. The characteristics of waves, or the way that we can analyze wave, remains the same. Sound wave and light waves, they are the same. Only the difference is frequency. If I say some, and then if we see this wave sine curve, and therefore you can count the cycles of your sine waves, the number of cycles is nothing but the frequency. So number of cycles per second means a frequency, so-called hertz. Everyone now knows 2.4 gigahertz, right? That is a very typical the frequencies of your iPhone, smartphone, Android phone, whatever the phones that you have, right? Or 10 or 15 years ago, at home, you have 900 megahertz cordless phone. Do you remember? Anyone remember that? Right? 900 megahertz. It was very expensive at that time. Almost $1,000. Yeah, almost $1,000, right? But it didn't last long. 900 megahertz cordless phones. If you purchased that 15 years ago, I think I paid, or not $1,000. I think I paid $200-300. Only that phone is not smartphone. It's very big. What it does is that if you have that and then there's a base phone set up inside your home, and then you can carry another cordless phones. Then you can walk outside the backyard you can still take the phone, right? So that is a big advantages at the time. The frequency used for such phone is 900 megahertz. 900 megahertz means waves vibrates. How many vibrations? 900 meg, then 900 million vibration. Almost a billion vibration per second. Sound, the vocal sound that we can talk, it's not that high frequency. Only a few thousand, at most 20,000. If very young girls shouts, screaming for a couple of seconds, then it reach up to like 10,000 vibrations. Men, maybe a few hundred vibrations, which is far from 2.4 gigahertz. 2.4 gigahertz, how many vibrations? 2.4 billion vibrations per second. We cannot make it that quick, right? Because that needs that much energy. It needs that much energy. 2.4 gigahertz, it needs that big energy. Example that you can see it has that big energy is from your microwave oven at home. The frequency is 2.4 gigahertz. When you turn on microwave, then that is some waves coming from top to bottom. 2 billion vibrations. Therefore, it penetrates some of the meats and then cook the meat. It's not really cooked, right? Warm, right? What microwave can do is warm, right? Because some of the atoms and molecular atoms moves so fast because of that fluctuation, vibrations, therefore heat up. There's a microwave. Anybody touched inside the microwave while it is on? It's cooked. Therefore, there's a door. It's not working unless you close the door. Only possible you can feel is that cut back. But anyway, it is high temperature. High temperature means energy, big energy. 2.4 gigahertz means big energy. It can warm the meats. Even if you talk so fast, you cannot heat up anything, right? If you talk so fast, therefore you can heat up your coffee. If you could, then it is like this light. Light's frequency is a lot faster. Sunlight's a lot faster. Anybody heard of the speed of sunlight? How fast it is? Sunlight. It can traverse the globes about 8 times per second, right? 8 times. Energy, big energy, right? Okay, sound wave can be counted as a particle. Here it says particle. Without having any objection, we simply say, oh, here is a sine wave, sound wave, and also particles. As I said, 300 years ago, particle and waves, then there's two different characteristics. Particle then can be is more distinct objects, right? Waves is more continuous objects. How come one thing can be treated as a continuous, another thing? I mean, the same thing can be treated as a distinct or discrete, but they are the same. So sound wave is nothing but a particles attached to and also interconnected particles interconnected. Therefore, some other analysis we can say that that is a wave. Sound wave may collide to transmit energy, collide the space media, hits. If your sound hits water, water is more dense than air, right? So it collides a lot. Therefore, it uses energy, consume waste energy. So the energy, the wave may decay quicker. So you cannot transmit your voice message under the water longer, right? Have you talked to your friends under the water when you do swim? You could do, right? Usually, but they do not hear. They cannot hear you because it decays quicker. Yeah, that is another, right? We cannot make clear sound. But in the air, okay. What about outside the earth? There's no air. We can go a lot further because there is no resistance. Think about this. From Mars, how far is it? Longer than 100 miles. Very far, right? But from NASA, they can receive the signals continually, very quickly, right? How come it is possible? Because there is no resistance. So with a little bit of energy, that, for example, image, photo image can be transmitted to the Earth. When it comes to Earth, then maybe it needs more energy, so it may decay. But depth of our air is not really big, therefore NASA can receive it finally.
I have a question on this. So, how do you differentiate between sound wave and echo?
Oh, we'll look at that echo a little bit, right? Echo is reflective energy, right? There's another physical symptom of sound waves transmission. If there is a wall, and if your sound has enough energy, then the thickness of the wall, then it can penetrate. Otherwise, it reflects. Or sometimes partial penetrate, partial reflect. Therefore, depending upon where you live, if you live in an apartment and your neighbor, depending upon the material of the wall, you can hear or you cannot, or partial, right? That happens. So echo is completely, not almost completely reflects. And then when it reflects, there's one thing. If you have the exact same characteristics of the waves and it reflected, then there is another collisions. You're sending out a wave and reflected waves. So sometimes it may decay, disappear by itself. But echo is not that type of things, right? It's so like a reverberance. Some sound maybe reverb, or echo. Echoing is the same. When it echoes, it is not really exact same sound. When it echoes, you hear a little bit different, right? Therefore, it is not decaying. There's no um, distortion or collision. So a little bit of a different characteristics. Reverbs and echo. If it echoes, then energy is preserved. But pitch or loudness is a little bit distorted. Therefore, echo sound is always a little different, but looks like very clear, right? If we shout in some valley, okay, Hudson Valley. Hudson Valley is too wide, so we cannot usually, impossible to get echoes, right? If we have narrow valleys, then you can get echoes. It should completely reflect, almost completely reflect. To, in order not to make echoes like classrooms, then some materials absorb their waves so that a little bit of echoes. And depending upon the materials, it may bounce back with no change of that waves. Then depending upon the phase of that waves, it may be strengthened or decayed. Such physics are more elaborated, therefore finally they make laser ray laser. So we'll do that maybe at some other times. Rarefaction, so particle separation, sometimes strengthened or sometimes a rarefaction. And then sound wave is a longitudinal wave, which means some of the fluctuation, vibrations, like this. So like a condensed or rarefaction, by using characteristics of sound, by using the particle concept of sound, when the particles is transmitted, depending upon the density of the particles, we can say there is a condensed or rare. Therefore, it's very likely can be drawn as a sine wave. We call that sinusoidal waves. If that is condensed, then it's more higher amplitude, less than low amplitude, high amplitude and low amplitude. In elementary physics, you do that, right? A little bit of that experiments, tuning fork hit that, and sometimes you can hear uh, uh, the repetition of the big sound and the weak sound and strong sound and weak sound and strong sound. Do you remember that? Right? Why? Because there is a two. Um Here is this guy generates, and also therefore this guy generates. So two signals comes together. So at some phase there's more strength. At some phase, both canceled each other, therefore very weakened. And at another phase can be strong, strengthened. So strong, weak, so that we can hear different strength. So by having that experiments, we can see sound is a kind of sine waves. So by having this, Newton says, oh, light is also particle. Actually, if you have a very small slit and send out the lights, then after that you can see some distortions, particle distortions. It's not like waves. If it's waves, then waves go out, right? But through small open spaces, the other side is the light. This side there is no lights. Then you can see some particle dispersion, some movements. So if you think of a particle, then particle can be collided. So collision or rarefaction, collision and rarefaction. Particle P1 and P2 and P3, they are moving along the same directions. But depending upon the speed of the particle, energy, movement energy, P1 may reach faster to the position where P2 is, therefore collision occurs. Okay, that happens. So sound waves can be generated and further propagated. Sound waves is nothing but changes in pressure caused by vibrating objects. Condensed, in other words, compression, right? Particles are compressed, or some rarefaction. If there's a compressed, then high pressure. Why high pressure? Particles are moving a lot within that space. It hits the boundaries a lot, therefore high pressure. Last a few weeks, when we had very cold weather, your car, your vehicle's tire pressure. Did you have some warning signs of flat tires all the time? Because it is not because of the flats, but because of different level of pressure. Your wheel, okay, there are airs inside, and then you keep the pressure of the air. I don't remember the pressure, but maybe 35, 32 psi, right? Psi. Pressure, psi. I don't know what that stands for. But anyway, So air should move within that wheel. So it moves, the level of movement is called the pressure. If you have more airs, then they collide each other, so a lot of heats inside. When it comes to cold weather takes out some of the heats from that air movements. Energy is reduced, therefore less movement of airs. Sometimes you can feel, oh, there's tire is a little bit flat, right? A little bit, or unbalanced. So all four tires not necessarily have the same pressure. Therefore, if you have uh, cars with the current technologies, then each tire wheel there is a pressure sensor, pressure detector, air pressure detector from each wheels. It's sent to the microcontroller of your car, and microcontroller compares those four sensor data. If there are some mismatches, then turn on some indicator, flat tire. You see that, right? So current cars is that. Oh. There may be some other cases, your mechanics carelessly take out that sensor from your wheels, then you don't feel that indicator. It doesn't mean that your car is not necessarily being flat. It means there's no sensor telling you that your tire is flat. It is so dangerous, right? If you lose some of the sensor, air pressure detector sensor from your wheels, any one of those four wheels, then it is very dangerous, right? Especially you rely on that, oh, there's no indicator on, therefore you feel that, oh, my car is okay, run fast with the flat tires. You lose not only your car, but also some other values. So there is another sensor technologies, very, very old sensors technologies, right? If you see the current vehicles, then you can see a lot of sensors embedded. What are the sensors that you can see? Anybody has a brand new vehicles? 2015 vehicle.
Proximity?
Proximity, yeah. If you reach somebody's, then it can give you some warnings. Or somebody approach to you, then warnings. What else? GPS, right? Very common. All kinds of cameras. Rear back-end camera will be mandatory sooner or later, right? As far as I heard from news, I think from 2018, all the cars manufactured in the US or sold in US should have rear cameras, so that when you pull back your car, you can see behind. So camera technology is another sensor. Somebody might say, oh, it's not censored. Why not? It takes light information. Photo is nothing but light information. Because there is a light, camera can take it, right? We call that visible light within some frequencies. But anyway, we will get that point later. Sound needs medium to vibrate. Speed of sound depends on the medium. So we can say air is 1130 feet per second. In the water, 5,000 feet per water. Oh, it's a lot. It reaches further as far as you can make. Water is still 13,000 feet per second. It reaches a lot fast, a lot further. Yeah. How can you see that? Yeah, they're so dense. So it once sound is in that media, then it reaches further. But media, I mean, sound comes from outside, then it's very hard to get in the metal, for example, steel. But sound generates in the steel, then it reaches so further. Similarly, water, if you make sound inside the water, previously, like while swimming, have you talked to someone else? Of course not, because we cannot make sound. But once you make sound, it reaches. But when you make sound from outside, let's say your daughter is swimming in the underwater, okay? Under the water. You are outside. If you call your daughter cannot hear you because different media, when it reaches to the water, higher density than air, bounced. Very hard to penetrate. Little bit of a sound may penetrate. Or if you put more energy, then it may penetrate a little further, but usually not. So that your daughter cannot hear you, right? So what it says here is if it generates inside the water or inside the air, then it reaches 1130 feet per second. 1130 feet per second. So if we shout here, then maybe if there's no obstacles, right now here Manhattan campus, if I shout, and outside there is a Macy's departments, maybe that is about 1,000 feet. So somebody can hear me. If he can hear me, he can hear me in some time delay. How much? 1 second. If it is 1,000 feet away. If there is 2,000 feet away, then how many seconds time delay? 2 second time delay, right? If he can hear me, but depending upon the energy of your sound, may not, right? Thunderstorm, for example, it has a big energy, right? So sometimes you can hear it reaches to your ears, right? But it reaches a lot later than thunder light itself. Right? Lights a lot faster, sound very slowly. In the air, only 1,000 feet per second. But if there is a thunder under the water, then you can hear it a lot faster. So under the water, if there is a bomb explosion, then submarine can identify it a lot quicker. Therefore, may be able to turn, but turning submarine takes a lot longer than turning a car outside, right? Because water, it has resistance issues. Any question, comments? So now we need to measure. Sound waves are longitudinal wave. So it's some vibrations. Vibrating objects compress the air around it or disperse it. So push the air away, leaving an area of low pressure. As you can see here, some the animations, right? There's longitudinal waves. So maybe particles hits each other. Vibrating object compress more air, and then there's a chain of objects constructed. So how can we measure it? If you see, because of that longitudinal waves, therefore vibration, which means objects are pushed, and therefore the different densities occur. As you can see here, more density, therefore you might have high pressure, and low density, low pressure, and very nicely you have sine waves. So you can think of amplitude, frequency, and phase. Amplitude, depending upon the density here, you might have higher pressure and also lower pressure and higher pressure and lower pressure, right? If you have not even this many, or very, very rare, then very low pressure. If you have a lot more than these particles, then higher pressure. Depending upon pressure, you might have different amplitude, different height. From here, there, a height. Right? So we have different amplifier. Frequency. These particles are condensed and dispersed, rarefaction, condensation, rarefaction, condensation. More frequently, then higher vibration, more number of cycles. Rarely occur, then very smoothly. It means frequency. Frequency is the rate of vibration. More like a number of cycles per second. How many vibrations per second? That is called hertz, right? H-E-R-T-Z. What's the name of hertz? It's not English name, right? Italian? No. Greek? Holland? If not, let's say Korean. Just kidding. There's a frequency. Phase. Phase means this guy starts from here. At this point, it's condensed. Another sine wave It starts from here. So same waves like this, or like this. Little bit of a shift, right? We call that phase. So we can characterize characterize sounds in using those three measurements: amplitude, frequency, and phase. So if you have, I mean, having those three factors, sound or lights waves can be formalized. So electrical engineers formalize it to pi ft some theta plus psi and so on and so forth. It covers all of this: amplitude, frequency, phase, which means mathematically we can analyze all different waves. Okay, but we don't do that here. Cycle. A single push and pull of the vibration objects. So one cycle is a compression followed by another rarefaction. So it can be depicted in two-dimensional spaces. So x-axis represents time, y-axis pressure. Therefore, we might have some cycles like this, wave cycles, right? So from here, it repeats, which means it vibrates, and it, when it returns the original shape, it is called one cycle, right? It's a cycle. And frequency is the number of cycles per second. So we can say cycles per second. So if we have more frequency, it means more cycles. Hertz here, it's the name of a person who initially tossed the point of that concept. One cycle of a vibration is called the period, which means time elapsed per cycle. This is a cycle, beginning of a cycle. This is the end of the cycle. What is the time elapsed between these two? It is called the period. You can say T. Okay. The unit to measure the period is again the second. So one period is half second. Then what is the frequency? One period is 1/2 second. Then what is the frequency? Which means from here there it takes 1/2 seconds. So frequency means how many cycles per second, because one cycle takes half per second. We might have 2 cycles. it is called 2 hertz, right? If one period of wave is 1 second, then that is 1 hertz. 1000 hertz means hertz means the period is 1 millisecond. Milli? Micro? It's not milli. Milli is 100th, right? Micro means 1000. A milli is 1000. Micro is 1 billion. Yeah, maybe. No, 6. Milli. I mean, milli is 1, 3, and then micro 6. Nano. Yeah, nano is 1/9. Yeah. So 100 hertz means the period is 10 milliseconds. It takes that long. The lower the frequency of a vibration, the longer the time needed for a complete cycle of a vibration, of course, right? Low frequency, then needs more time to get to. Right? If it takes one second per cycle, which is very slow, therefore low frequency. High frequency, it moves so fast. More movement, which means it has more energy. Back to my earlier explanation, therefore, microwave oven, 2.4 gigahertz. What is the period of that wave? One over 2.4 nanosecond. Very short. One cycle, which is very quick. Therefore, per second, there are billions vibrations, which is energy. Can heat up your food. Vocal frequency of vocal sound. Woman's 240 hertz, usually 240 hertz. Man 120 hertz. So woman's let's say same amount of talk, man and woman, who get tired easily? Woman get tired easily. Yeah, it's double. You spend the double energy. Question.
So you're speaking in terms of projection, right?
Wave of vibration.
Okay.
Wave of vibration. Make high vibration, then it needs more energy. Of course, if you want to make this, it needs more energy, right? If you do this, I mean, by your finger, if you do this, you don't feel any, right? If you make like this, then. What did you say? Say it again. No, I didn't say that. The same amount of talk. Women spend more energy. Yeah. I'm not sure. Maybe the reason women get tired a lot quicker, right?
There's a big difference. 8.3 and
Yeah, double.
4.2. Now it's can
But energy is not all. Uh, if you get angry, then you need to put higher amplitude, right? It's more energy, higher amplitude. Human can hear 15 to 20 kilohertz. This is the sound generated by from our mouth. From our mouth. Our ears is more tolerable than our mouth. Our mouth can make only that limited hertz. Ears widely open, so that very small and very loud also, right? But human acoustic, human generated sound is somewhere in this range. But we can hear a lot other extreme sound that we cannot even make. For example, some traffic sounds. Can you make that traffic sounds from your mouth?
so. I mean,
Maybe some comedians mimic that, right? But not our normal tongue vibration.
so is this normal? Like, take it for instance. I'm like we're recording, and we having a conversation, right? But I'm right there, and you're talking very loud.
Hmm.
That's normal.
It's called pitch, right? So pitch relates with the amplitude. I think a high amplitude is a higher pitch. Usually it comes from women's than men. Men is a lower amplitude. Um, yeah, I we don't. Yeah, we are not studying deeper about the sound or lights, but I wanted to have some feeling. So frequency is very, very important.
So you're something like this attention of the memory. You guys close to the conversation because it's so loud. And you're right there. I mean, I'm not even happy with this. I'm just curious.
Yeah, if you have a bigger room, then instructor needs to speak loud so that put more energy. So my acoustic information wave should reach further, right? Yeah. So in theory, we can compare period and frequency. Then we might have that formula. Frequency is 1 over period. If we have 1 second period of a wave, then we call that 1 hertz wave, right? They are the same. 1 second period wave means 1 hertz. Half a second period wave means 2 hertz. 1/10 second period of wave means 10 hertz. 100th second period of wave is 100 hertz, according to this formula. This is what we talked so far, right? This is formula that we talked. We just formalize it, which means, yeah, here we already talked that, right? 1 million, the period of one cycle takes 1 millisecond. So F equals 1 over T for period, right? So if you plug this 1 millisecond here, then 1 over 1 millisecond, which means 1.001 seconds, which is 1000. So we looked at that. High frequency means high pitch, more vibration. High pitch means, yeah, high pitch means high vibration. I take it back. I explained that with the amplitude, right, minutes ago. High pitch is not necessarily high amplitude, but high vibration. So ladies make more frequency, more vibration of that acoustic sound, more vibration. It's not like a higher amplitude. Octave, octave. I think in Italian it is called octave, right? Or octave. Octave. So doubling of having have. How to pronounce this?
I can't believe it asked the English major.
Having of frequencies. So octave, one octave is doubled every time. So you can think of that. For example, I have a slide here. Piano or violin. There's an octave, right? Octave. Every how many? 8, right? So 2 to the power 3. But they're all about frequencies. So if you go here, let's see. How can I get? Okay. If I click this, then you can see this is a piano, right? I guess, right? Sound. So for example, this is standard key A4. A chord from how many octave? I think 4th octave from the bass, which is here 27 hertz. If you see the piano key, then that is very low level. I'm not good, but I wanted to think of that. Okay, so this is that one. A4. Key number 49. We call that A, key A, but octave 4, 4th octave. The frequency for that is 440. That is a standard pitch, I guess, standard, like this. So this is the standard here. And another key G, and this black key, short key, is a little bit above from G, a little bit lower than A. So we have sharp and flat. Looks like that I know more than you. I don't know anything about this, right? Yes. So there is a standard key. They are not the same. A flat and G sharp in frequency not necessarily the same. See here, this is 415, little bit lower than A key, little bit higher than G key is 391. Look at these two keys. Frequency, in theory, frequency should be different. But in implementation, instrumental implementation, if you want to make piano keys, then we need to choose one or the other, or average. That is called standard average or something. I don't know. There is a who made that? Beethoven make some standard something, right? That's what it is. Actually, they are not the same, but in real instrument, we make average and make the sounds. This is piano tuning. It's not the same as a violin. Violin, there's no discrete frequency setting. Violin, you can push any string, right? Piano, you cannot make sound somewhere in between, somewhere not this, but little lower than this and little higher than white, little lower than this black key, little higher than this white key. There's no such mechanism available in piano, right? Piano is limited, predefined frequency sound can be generated. Violin is a little different. All possible. Therefore, what? Traditional orchestra would tune based on violin, not the piano. Why? The piano, all the keys are limited. There's no in between. You cannot make. I think that is too much to us. But anyway, what we are going to say here is we have the frequency and then wavelength also. What is wavelength? The distance between the cycles. Distance of cycle, one cycle. Period means time, elapsed time. Wavelength means it is a length. So the frequency can be also, this is a frequency. I want you to think frequency can be formulated based upon period, right? Period here, denominator, and 1 over t. Same frequency can be formulated, in this case, based upon elapsed time, in this case, based upon wavelength and speed, velocity, speed. Waves, then there is a speed, slow speed and fast speed. Sometimes some sound can reach a lot faster. Some sound may reach very slowly. This is velocity. If you have same, let's say, same wavelength, For the same wavelength, wavelength is already defined if there's a wave, right? For the same wave, which means the same wavelength, higher frequency fast or low frequency can run fast. Higher frequency can run fast or low frequency can run fast. High frequency can run fast. As I said, this is fixed. Wavelength is fixed. If this goes high, then this goes high too. If this goes down, this goes down too. Right? If you have very, very, very high vibration waves, then it runs so fast. So what happens? Usually, woman's shouting reaches faster or men's. When you call somebody, then who usually need to call so that somebody can hear faster? Woman or man? Answer. Woman. Why? High frequency, right? Double. Woman's shouting reaches, yeah, it runs double time, yeah. Oh, your wife's triples? Yes. Yeah. So if your wife shouts at home, then your neighbor can hear very easily. That happens. It's faster, reach. I mean, it's a theory. It's a mathematics. Okay. Amplitude, as we looked at, higher density of particles. So loudness. If you have loud means higher amplitude. Loudness. That's what it says. Okay. Velocity, how fast it is, so like frequency. Whose voice is loud, women's or females? We do not know. That didn't say here in this slide, so I do not know. But not necessarily. Yeah, it's not. It's very hard to measure loudness, right? Pitch, yeah. Pitch means there is frequency. It runs so fast. Men's shouting sometimes very loud, right? You still make it loud so that your voice can reach their ears. Yeah. What time is it? Let's see. I think we need to finish up sound. Another thing is a decibel, some noise level of noise. Phase that we looked at, right? Oh, interference. You talk, your friends talk together, different language, then there is interference. So that the other person say, hey, I cannot hear you, one at a time. Or you can say, let me talk first. Interference.
It doesn't do it. Sometimes people know the rules of conversation, so sometimes it gets more talking.
We're talking about here physics only, not the semantics, like level of understanding the meaning, but the wave itself. If we see here two waves, they start the same phase, then it is a constructive interference. it multiplied. Same waves, but slightly different. In this case, exactly 180 degrees difference in phase. Therefore, they cancel out each other. What happens? Very interesting. This is a big weapon. This is exactly that we need to do for our cybersecurity. Some sound with some messages send out. How can we cancel it out? In theory, like that. So we need to nullify their communication. I think this is your interest, Chris. Chris interested in frequency. So what happens is that if there is some car key braking signals is generated, then we make another 180 degree difference frequency generated at the same time, then cancel out. I mean, in theory, we could do, right?
We can just generate the signal just with a different phase. So just generate
Same signal, yeah.
Same velocity and
Mm-hmm.
same
Exact same ones.
just postpone
It carries,
phases.
yeah, it follows that it cancel out. Speak defense or offense. Sometimes we can say beats, right? High beats, low beats. It's a little bit different. I wanted to read some of this. Okay, reverberance. This is not echo, but reverberance is related. Okay, if it is echo, then echo consists of individual, not blended sound images. Reverberance is a little bit of blended. The mixed sounds can be mixed. Therefore, we have different effects, like the way that we hear interference, then constructive or destructive. Absorption. Some obstacles may absorb the frequencies. Frequencies above 10 kilohertz tend not to bend around corner well or other obstructions. So 1.3 inches for 1 kilohertz tone. Well, what it does, this message says there is some absorption. Errors usually observe frequencies above 2 kilohertz. Animals can generate the sound in different frequency than human. For example, bird or some insect some generates their own sound which we do not hear. We do not hear much, right? But some animals can hear. I use that when I knew this at the first time. I was really surprised. No one told me this, but I found it. Woodpecker. Woodpecker. Woodpecker locates the trees very precisely. They never fail the worms inside the wood. Think about this. Woodpecker pack out the wood. Finally, if there is no food in it, then it's so useless, right? They work so hard. Did you see the woodpecker pack the trees? They pack with using all of their bodies. More likely their head. They head, I mean, bounce it to the wood, and then wood particles can. Um, but they know inside somewhere in depth there is a worm is moving. What woodpecker and why woodpecker make a hole to the wood is because I mean, for that worm eat it. How do they know? In the air. There's a forest. Few of those trees has the worm inside. Then they land it and they pack, right? They hear something that we never hear. Woodpecker can hear something we never hear. I think nobody here, the worms eat some of the tissues inside the trees. But woodpecker can hear. And also there's a wood, there's obstacles. The sound is very hard to penetrate to outside the air. So woodpecker is very, very sensitive to catch the movement, right? That I would say that's, I guess, here. Air tends to absorb frequencies over 2 kilohertz. Then what happens? The worms, a lot lower frequencies, maybe, so that it's not observed, so they can hear. I do not know. I studied that and I stopped. It's very, very interesting. Acoustic attributes. Another factor is the intimacy. If you have so crowded, or loudness, or liveliness, so all such things. Intensity. Decibel. What is the decibel here in this classroom right now? About 60, 70, right? Here's city streets. Higher decibel means a lot of noises. So quiet room in the library, maybe 10 or 20 decibels. Jet engine, 150. So sound, another measurement. Okay, so let's take a break, and after the 15-minute break, we will talk about lights. the physical phenomena of the waves very similar to sound. Why? Because we're talking about sine waves anyway. So frequencies, relations between frequency, velocity, wavelength, time elapsed per cycle, and formula formed over those factors remains the same. Okay. Speed in vacuum. Speed of what? Light. Speed of light. Light speed in vacuum is 300,000. Oops, right. 300,000 kilometer per second, which is 186,000 miles per second in vacuum. So light comes, for example, sunlight comes from the vacuum, right? There's no air. It reaches to us through the air when it comes to our globe. But anyway, 300,000 kilometer per second means the lights can traverse surrounding the globes, I think 7 or 8 times per second, that much faster. If we have airplanes operates that fast, then you can come to this classroom and go back home so quick. Speed on other materials like air, water, glass, slow, right? Lights also. This is a history. Newton, like almost 400, 300, 400, 300 years ago, Newton says light is particle. Maxwell, I think both of them are English, right? Newton and Maxwell. Maxwell is English name. Light is wave. If it is particle, how do you know that is particle? See here in this experiments. In this experiments, there is a little bit of slits, and this is a light in here and dark the other side. Therefore, you can see some of the particles. But Maxwell says there is some waves, and through another panel, then you can see some of the lines. Therefore, we can say that is wave. Richard Feynman, he graduated MIT and Princeton physics, and taught in Cornell University and Caltech. Why did I write this? Well, I was interested in him, so that I looked at his, I read his life. He taught at Cornell and Caltech. He lives in Queens. I think he was born in Queens, but he lived in Los Angeles, California. What he said, by taking these two contributions, and says light duality, which means light is not only particles, but waves. Actually, this is proved by whom? Einstein. When Einstein was where? Princeton. He was the physics professor at Princeton. So he got Nobel Prize winner. How can we see? how the light is the combination of major three lights, red and blue. We all know that. So if we have mix those three lights, then you can see some you can generate the lights. How many lights can be generated if you have uh, if you represent the color in 8-bit, 1 byte long? Don't get anxiety. So bytes is 8 bits. So color can be represented in a byte. So we could have, if we use only 1 byte, then 256 colors, right? But we mix the 3 colors to make a light color. What do you mean by light color? The color that we can see from monitor, that is a light color. It's not the color that you draw, you paint. Are you good at paint? You know how to paint, right? But this is a light color. Light color can be generated by, one color can be generated by 3 bytes, right? So different level of red, different level of green, different level of blue all together. Therefore, you could have about 65 million colors. If you represent 2 bytes per color, then terror, how can terror in digital concept? Where billion, right? Million, billion. After that, zillion, trillion, zillion, whatever. Colors, 1,000 zillion colors can be generated. We could generate as many colors as we can. Slightly different. We cannot tell the difference at all, or only we can see the difference in number, right? But anyway, usually, typically, 3 colors, so that we can recognize different colors. If we have 7 colors, for example, rainbows, by looking at the rainbow, then we can see, oh, light is nothing but the combination of colors. In general, you've heard of this in many times. The way that we can see, the way that we can identify the color of clothes worn by someone else, it's by light, right? Blue shorts, we can see, oh, how can you see it? How do you know that it's blue? First of all, if there is no light, then we can see anything. We can see some color because there is a light. Then what is the relationship? Then lights and the color that we can identify from some surface, from someone's clothes, because the light is reflected to my eyes. All other colors are observed. All other colors, absorption. Only color that I can see are reflected. Maybe multiple colors are reflected. Maybe one pure color can be reflected. So we can say that, oh, this black, which means nothing reflected. Black means nothing. All the colors are reflected, then that is a pure white. Look at lights, sunlights. You cannot see, it's already dark outside. See the sunlight. Then if somebody said, what is the color? Then how can you say? Can you say it black or can you say it white? Of course, there's white, right? All the colors in the lights that we call that white. If you have all the light colors mixed, then that is called white. If there is no color lights, no lights at all, we call black. If I have a black jacket like this, so that you call the color of my jacket is black. Why? No reflects, no color reflected, no color. This black color is exactly the same color as there is no lights. Right? As I said, how do you know there is lights is a color mixture? If you see the rainbow, you see the colors. What is a rainbow then? Rainbow is nothing but some prism. I want you to recall some of the science class in elementary school, and then there's some prism, and then your teacher lights, and then you can see all kinds of colors. After the rains or during the rains, there's some moisture depth in the air, which works like a prism. The other side of that, there is a sunlight. Sunlight passes through this prism. Therefore, this one end, there's only light. The other end, you can see all kinds of colors. Those all kinds of colors, to human eyes, only 7 colors. We can identify only 7 colors. It doesn't mean that there are 7 colors only. How many colors? Millions, zillions of colors there. But we can see only. Why? Because our eyes is not that sensitive, right? Sensor that we will look at second half of this class, some of the sensors can identify the color. A lot sensitive than our eyes. If you install that sensor to find out, for example, some terrorists who wear some color, our eyes, we do not know. It's very tired. Oh, I cannot see. Sensors keep looking at, right? There's a light. Very similar to the sound. The only difference here is that it's color. Light has color. Well, somebody said voice has a color also, but that is not the color that we could see here, right? Lights. Then why do we say about electricity or magnetism, magnetics, electric? Color has energy. That energy is electromagnetic field energy. Where there is electric field, there is energy. Where there is electric field, there is a magnetic field as well. So, I'm looking at the charge in motion, it's magnetic fields. Okay, static distribution of charge produces an electric field. Charges in motion produce a magnetic field. So from one energy, then we can see both fields, electric and magnetic. Changing changing magnetic field produces a electric field. If there is a current, electric current, then there is a magnetic field. Magnetic field means there is a motion. So the other way, where there is electricity, then there is a magnetic field. Okay, but we can think of the other way. Supposedly, if there is a magnetic field, therefore we could have electric field. We can generate electric field. Electric, right? Electric. We can generate some electric. Electricity, then we can, oh, electricity, then we need to buy it. Is there any way that we can generate electric field? Yes, if we have magnetic field first. Magnetic field is nothing but the motion. Look at that red color, charge in motion. Where there is any motion, then it means magnetic field. Once there is a magnetic field, automatically there is electric fields. Remember that last class we said, if you walk, by walking, walk means what? Motion, right? Change of motion. Therefore, we could see, oh, then we can generate electricity from some motions. There's some work, some research is going on, right? Let's say we, here in front of Macy's in Broadway, a lot of pedestrians walk. If we take their motion to create magnetic fields, then there is an electric field. Electric field means there's electricity. So as they walk, we use electric fields. What is a motor? Motor can generate electricity, right? Motor needs some spins, right? Some movement. If there's some rotation, high movements, therefore it can generate electricity. Long time ago, when I was young, when I ride the bike, then bike needs headlights, but we do not use batteries, but there's a bike wheel, and then there is some mechanism. It rotates as we roll the bike, and all of a sudden we have lights, right? That is exactly what this means. Where there is a motion, it generates magnetic field, which means electric fields. So all the electricity generator starts from some movement. Electric and magnetic fields produce forces on charges. An accelerating charge produces a electromagnetic waves. Yeah, they are all same concept expressed in different ways. Both electric and magnetic field can transport energy. Where there is electricity, if you construct a magnetic field, then at the other side, there could have electricity also. We all know that. That is connectless phone charger, right? Phone charger, we do not really plug in, but some pad where there is electricity. You place your phone on top. This side there is electricity. Place your phone on top. It's not really connected, but there is a magnetic field constructed. Because there is a magnetic field, this device, untouched device, also has electric fields, which means same voltages, same electricities. That means charge, right?
So you can Starbucks. They have it now.
I've never used it. I've never seen it, but I'm talking about in theory,
Now they do
where
have
there's a Starbucks
in
outside.
Starbucks. You just have a electromagnetic field. You
Uh,
can just
Place your
yeah, place your smartphone.
oh, I see. Yeah. Theory behind that is this. Okay. Electromagnetic fields. Then see, there's some orthogonals, right? You have this. Let's say this is electric field. Then magnetic field is always this orthogonal. Any, it doesn't matter, right? All orthogonals. So electric field flows this way. We call the current. Electric flow. What times? Need to check. This. If electric field flows in this way, then there's a right arm law. Is it right arm law? Right arm law. There's a law principles. So that that is the direction of the current. So magnetic field flows in this way. If this flows like this, then that is magnetic fields like this. Magnetic fields means from north to south there is a magnetic field, right? Back to your elementary school, there's a magnets, right? Magnets, there is a north and south, so that stick together or they bounce each other. If you have the same magnetic, right? You know that, right? That north-south constructed in this way. So from north to south, like this. Okay, we have light speed 3 times 10 to the power 8 meter per second, which is 300,000 kilometer per second, almost 187 miles per second, right? So there's a speed. Example of electromagnetic radiation, we have AM, FM radio wave, cell phone communication links, which is 2.4 gigahertz. Similar frequencies, microwave, 2.4 gigahertz, right? And then there is infrared radiation, infrared. And we have light. This is from low frequency. Here, low frequency. This is a very high frequency. For example, gamma ray. Anybody can see gamma ray? No, you cannot see it. How can you see gamma ray? We don't even see X-rays. Healthcare, if you could X-ray, then do you see X-rays? Oh, there's a flaws. Watch out. Microwave. Anybody see microwaves? Turn on microwave. Oh, this is very strong. AM, FM radio. Oh, we have some signals coming here. You don't see it, right? None of them cannot see. Which ones only can see? A little bit of this. here red, from red to violet, right? So all the way here. Typically, we can say that is a rainbow color from red, a little bit of purple somewhere here, right? And blue somewhere here. Those are all the colors that we could see. We call that visible color. Any color, any waves in little lower frequency than red is called infrared. Any light, any waves little bit higher in higher frequency than violet is called ultraviolet. So UV, right? UV signals, waves. Medicals equipment use a lot of infrared radiation or UV, or even lower than this, we have sound, right? Sound that we could see 220K, that is our audible sound. But a little higher than that, we call that ultrasound. Ultrasound is a lot lower than AM, FM radio frequencies, but a lot higher than our acoustic. Okay, that is ultrasound. The ultrasound can penetrate our skin? No, cannot penetrate our skin. Therefore, we need to apply some ultrasound cream. Yeah, so that cream absorb ultrasound frequencies. So all science, right? You see all spectrum, right? So all the way up, very low frequency that we could hear. Low frequencies, man can talk only 200 or 120. What was it? 120 hertz, right? And ladies 240 hertz, and all the way up, and then there is a ultrasound, and even further up, then there's AM, FM, cell phone, microphone, and all the way to gamma ray. Then where is the laser? Laser is somewhere there. Very high frequency, but it is not, doesn't exist by itself. It is invented. All other frequencies exist. We use it. Laser, that is a product of our science, right? So laser also used for medicine, medical treatment, war, laser gun, laser something. Eventually, our cell phone signals may be on the laser signals than microwave, a lot higher. Then that is ultra high speed cell phone. Okay. Okay, let's have next week.